Hello everyone, this is Doug, and in this video I'm going to talk to you about Dieball versus LAH when it comes to the reduction of carboxylic acid derivatives, right? So you should also think about this video as a video on the reductions of carboxylic acid derivatives. All right, from your acyl halides down to your nitriles. So these are the two main actors. We have Dieball, which is diisobutyl aluminum hydride, and LAH, which is the lithium aluminum hydride. And we already know LAH, but Dieball is kind of the newcomer here. The big difference here is that Dieball, which is this molecule on the right, only has one hydride. So it only donates one molar equivalent of hydride, so you don't have these multiple ones, right? So what's going to be really nice and really key about Dieball is that if I have a molecule like, say, this acyl halide, Dieball, so step one for Dieball, is that it's going to donate the equivalent of just one hydride, right? So this will kick up, and then like we talked about before, I'll show you more mechanisms in a second, so green would be second, that you kick up, kick down, and what you end up doing is making something an aldehyde. Right, and then step two, and I'll show you this more later, step two is you need some water. But the big key thing here is that you form an aldehyde. That is really what Dieball is all about. It's the main use of Dieball. Dieball gives you aldehydes. That's really why we use it. So I'll put Dieball is a great way to reduce to an aldehyde. Now, in contrast, right, LAH, like we talked about before, we've seen LAH reduce aldehydes and ketones. So I know I'm not going to be able to stop at an aldehyde because we know that it reacts with aldehydes. LAH, right, has these 4 hydrogens on it, these 4 hydrides, and it really gives you a little bit more. Studies show that it's about 3.2, 3.3 equivalents of hydride ions per 1 mole of LAH. And so that's going to reduce things all the way down to having just one bond to a more electronegative element. You notice with the aldehyde, right, I have 2 bonds to a more electronegative element. I have 2 bonds, 2 CO bonds in that case. What's going to happen is if I took that same acyl halide here, and I used my LAH, so I've got my lithium aluminum tetrahydride, I'll say THF. Second step, I just need to add water. The idea here is that, right, your LAH is going to donate the hydride, that's true, and you do your same addition elimination. Again, I'll do the better mechanisms later. But you're going to do the same addition elimination step so that you form an aldehyde. But since the LAH has more than one equivalent, and we know that aldehydes are very, very reactive, what happens is that the second equivalent, right, of these 3 will then add in to our aldehydes, and then you end up reducing it all the way. Right, so you've added a second equivalent, and then you have a water workup step, some sort of workup step to give you the alcohol. Right, so what you've done, you ended up doing here is that this LAH with its 2 hydrides, you've donated 2 H's to that carbon, so you've reduced it twice instead of Dieball up here, right? Dieball just had this 1 hydrogen, so you added just 1 hydride to make your aldehydes. That's one of the bigger differences between them. Other differences is that Dieball, right, if you look at the molecule, it's not ionic. It's just a molecular compound. It's much less polar, so you can use it in less polar solvents. It works in things like THF, but you can use things like hexanes and toluene and stuff like that. Whereas LAH is an ionic compound, so you really kind of have to do it in ethers, things that are more polar, so THF, diethyl ether, stuff like that. Dieball, I'll just say this now, Dieball can reduce aldehydes, so you really have to make sure you use just like 1 equivalent, but it's a nice alternative hydride donor to LAH, which is super reactive. Dieball is very reactive also, but delivers just the 1 hydrogen. So let me show you some of the mechanisms, right, behind how Dieball works. So I think on that other one, I showed you an acyl halide, so I'll draw another acyl halide just so we can see what that looks like. So imagine we have an acyl halide, and I'm going to add Dieball, right? Step 1, Dieball. Step 2, water. And so I'll draw my Dieball, which again is just aluminum with a hydride, and then 2 isobutyl groups. All right, so I've got my 2 isobutyl groups. I'll put my partial charges on my molecules. So it definitely looks like, right, if this is going to be, and then let me add, so right, so partial positive, partial negative, partial negative, partial negative, right? Aluminum is less electronegative than hydrogen or carbon. And so what's going to happen here is that my oxygen is going to be attracted to that aluminum, right? The oxygen's partially negative, the aluminum's partially positive. The chlorine is also attracted, but it's not going to stick as much because chlorine, well, you will see in a second, the oxygen is going to become positive, and that's better able to be positive than the chlorine is because it's resonance stabilized and because of electronegativities. So my first step is going to be chelate with the aluminum. Basically, it's just a Lewis acid acid-base reaction. So now I've got my aluminum attached. This becomes positive, the aluminum becomes negative. I still have a chlorine here. So now this molecule is much more electrophilic, right? And if I draw the resonance structure of this, you can see that this carbon down here becomes fully positive. So I've got my LAH, which is still negative. So what we've done is, it's kind of, sorry, not LAH, the Dieball. LAH came with the aluminum already negative, and so it already wanted to spit out a hydride. For Dieball, it comes neutral. It doesn't want to spit out a hydride yet. It doesn't want to spit out a hydride until we get to here, right, which is where we add the oxygen to the aluminum. Now the aluminum's negative, so it wants to get rid of that hydride, right, or that hydride becomes activated. And so the hydride, of course, is going to go where that full positive is. It's going to be attracted there. You could draw the arrow from the bottom resonance structure, or you could draw it from the top resonance structure. Either one is fine. Whichever one you pick, you get the same thing, namely that the oxygen is now attached to the aluminum that has your 2 isobutyl groups on it. You have a chlorine here, and you have a hydride here. Now this is where the water step comes in, right? So all of that would be step 1. Step 2, I'm still kind of debating how much I want to show you of this. Step 2, yeah, I'll show you. You guys are smart. You can handle this. Step 2, the idea is that you add water. So you just sit here for a while. If in step 2 you add water so that water then attacks this aluminum, we still have the chlorine, we still have a hydrogen, we still have an oxygen. But now my aluminum has its 2 isobutyl groups, and now it has water attached to it. And the aluminum is negative, right? So we got 2 things that are going to want to happen here. One is that the aluminum wants to spit something out again, right? So it could spit out the water, which would be going backwards, or it could spit out this oxygen with our chlorine, that whole organic piece that we started off with. And if you imagine that being spat out, what happens, and I'll draw this in 2 steps, even though it probably happens in 1 step, what happens is that you get your O- back, and then you have your aluminum with its water attached, and your isobutyls. And really, this probably happened in 1 step, but the idea is that you have your negative O again, and that negative O is going to drop down and kick out your chlorine, right? Because that's the best leaving group. And remember that for all of these reactions, we have that addition-elimination step. So it's kind of like this first part right here, or this step right here was the addition step. Right, this was the addition step. This is where the hydride attacked the carbonyl. It added to that group. And then this step right here that I'm about to draw, right, that was the elimination step. It's eliminating that chlorine. It's an elimination step to give us, like we were saying before, the aldehyde, right? So we've made our aldehyde. So it's an addition and elimination. Other side products would include hydrochloric acid and then this aluminum oxide. You'd have an oxygen probably double bonded to the aluminum or single bond to the aluminum with the two isobutyl groups on it. So this is the general mechanism of how it works, right? First, it's going to chelate to one of those carbonyl oxygens, the carbonyl oxygen that activates the hydride to leave. That hydride's going to attack the carbonyl. And then through a series of steps, which I'm not going to personally care too much about, water adds in to release the aluminum and then regenerate your O- that then drops back down. That's the idea here. Now, this general mechanism works for, and you can look in books or online to find mechanisms for every single one of them, but the idea is this works for all of these carboxylic acid derivatives, right? We're starting up here with the acyl halides, right? We've got our acyl halides, we've got our ester, we've got the amide, and we even have our nitriles. Right, even our nitriles. If you take any of them and you add your equivalent of Dieball, you follow it up with the water workup step, you're going to make the aldehyde. That's going to be your main product. Now that I should note that in reality, the esters are a little they're a little so-so, they can be kind of messy, but acyl halides generally behave pretty well. Amides behave pretty well. Even the nitriles are not so bad. The nitriles, I will make a note here. Nitriles, you notice that I did add acid, and that's because for the nitriles, what happens is as an intermediate, you get kind of an imine. So you get the H that was added, but you end up with this imine like intermediate, so you need to do the hydrolysis. You need to do the hydrolysis of the imine to get your aldehyde back. But you all are already aware of that. You already know about imines and enamines and those reversible reactions being hydrolyzed. So, but the point is you can use Dieball to turn these back into aldehydes, right? You can reduce them to turn them into aldehydes. Now this reactivity is very different, right, from LAH, which was quite a beast and reacts like crazy. I should also say while I'm talking about reacting like crazy, if you do ever use Dieball, you want to treat it with care because it also is very sensitive to acids, right? It's still going to be very basic. You'll still make hydrogen gas, which is flammable. You just want to be mindful of it, right? It can catch on fire and everything. So if you use Dieball, definitely be careful with it. LAH, though, is a different beast, right? Dieball only donated one hydride. LAH is going to donate 3+. So it's going to kind of go crazy here. So what you end up seeing, right, is where LAH has these 4 hydrides on it, what it ends up doing is it ends up adding 2 equivalents to, for example, when you try to reduce an acyl halide. So your acyl halide gets reduced all the way down to the alcohol. Right? Notice that you just have one bond to something more electronegative, right? You just only have one CO bond. Same thing if you have an ester. Esters are going to undergo the same thing, right? You have these hydrogens, they are also going to add 2, and you're actually going to get the same alcohol. Also going to reduce you down to the alcohol, and I'll draw a mechanism for that in a second here. Now, amides are a little bit different. So amides have this different, they have a CN bond in them, which is stronger. And so for mechanistic reasons, you actually reduce it down to the amine. But you are still adding those 2 hydrogens, right? Those 2 hydrogens right there end up being the 2 hydrogens that reduce away that carbonyl. It's just that you end up with the amine that you added. Oh, and I drew the wrong amine. Sorry, this should have been, ignore this. Not that amine. It's really going to be the amine. I had an ethylamine here. It's still an ethylamine. Should still have that ethyl there. I accidentally just wrote NH2. That is not the case, right? Since there was this ethyl piece here, that stays. It's not like it magically goes somewhere else. And then lastly, we have the nitriles. The nitriles, same story. They're also going to be reduced down to the amines. And in this case, they will always be a primary amine, right? Because there was no R group on that nitrogen to start off with. So it's just going to pick up those 2 hydrogens, right? So these 2 H's are these 2 H's. So we get very different things if we use LAH. Notice that in all of these cases, the product was reduced down to just 1 carbon more electronegative element bond, right? CO bond in the first one, CO bond in the second one, CN bond in the last two. So it reduced it so you just had one electronegative bond. Whereas with Dieball, you still had aldehydes, which was 2. So LAH reduces further than Dieball does. Let me show you a mechanism of at least one of these LAH reductions here. So let's say we do have one of those esters. And let's say it's that OET one. Step 1, lithium aluminum tetrahydride, and say THF. Step 2, some sort of acid workup, water workup here. And so we're going to do the same thing. I'll draw all of my reagents out. I think I'll be a little more hand wavy with this one, just so that you can get the idea of what's going on. So here's how I'm starting, right? I've got an ester, I've put on my partial charges, I've got my lithium aluminum hydride, lithium aluminum tetrahydride. First step, right, is that, so this is already negative and it already has a full octet. So it's not like the Dieball where you have the oxygen go and attack the aluminum that didn't have a full octet. We already have one. So we can go ahead and just generate this hydride. It's going to go and attack your carbonyl carbon. Again, we're going to kick up those pi electrons because that's the weakest bond on here. And we're going to form, right, we're going to have an O minus and this O-ethoxy group and the hydride that we just added, right? You just added this hydride here. Now, realistically, well, I'll draw it. Again, you guys are smarty pants. So now you have this aluminum trihydride, which is neutral and everything. The O minus can drop down and kick out our O-ethyl piece, which gives me that aldehyde we were talking about, right? And ethoxide. And ethoxide. Now, this ethoxide could add back in, which is why this is reversible, or the ethoxide could go and add into this hungry aluminum, right? It doesn't have a full octet. It's looking for something, so it could add back in there. If you look online, you'll see mechanisms either where this like alkoxy thing, I have the epoxide, and not epoxide, the ethoxide. You'll see either the alkoxide attack the aluminum or the carbonyl oxygen attack the aluminum. Either way is going to be fine by me. The point is that it regenerates, right, your aluminum hydride donor. Right, now the aluminum's negative, and once again, right, we have an aldehyde. We know already that these reagents attack aldehydes. So this second hydrogen can attack, which is going to give me the O minus. And now I have 2 hydrogens attached here. And now the difference, right, again, I'd ask myself, well, can these electrons from the O drop down and kick anything out? And now the answer is no, because I have a CC bond and I have CH bonds, right? Those aren't going to get kicked out. They're terrible leaving groups. They'd be way less stable than an O minus, right? O minus is much more stable than H minus, or C minus. So that stays on until you do step 2, which is going to be your water workup or your acid workup. And again, that's just to protonate your O so that you get your alcohol. And I'll draw out these H's just to emphasize them. But right, the idea is that the H's right here and right here came from the LAH, and then the hydrogens from your water are the ones that protonated on there. And I'll draw this without those colorings. But you'd end up, right, with just your alcohol. So the mechanisms are similar but different in that Dieball just has one hydride to donate, period, whereas LAH can donate multiple ones. And you saw me do an example where it donated 2. The thing that it makes could then donate a third one in theory, but we're not going to go there. But that's a general mechanism for how LAH adds multiple hydrides to a molecule. Now some examples here. Looks like my first one, I have this amide and Dieball. Now, if you ever see just like Dieball written out somewhere, they mean to just use Dieball. Don't get hung up on the fact that it needs to have a second step, some to protonate stuff like adding water. If it just says Dieball, go with it. You should be thinking, oh, I totally need to make an aldehyde, especially given that I started with an amide. Right? If you have a carboxylic acid derivative like an amide, and you're using Dieball, you're going to turn it into an aldehyde. So I'm just going to redraw the parent and then slap an H on there instead. So I've got an aldehyde. Yes, you're going to make an isopropylamine, but no one cares about that. That just came off. You're probably caring more about the aldehyde group. Now in this second one, I have an ester, and I'm going all the way down to the alcohol. Which means it looks to me like I added 2 hydrides here, not just 1. So that must be the LAH. I must have added lithium aluminum hydride and done my workup step with water, right? Because I added 2 hydrides. That's different than here where I have an acyl halide. And I see that I'm going to an aldehyde, which again should scream that I'm adding just 1 H and that this must be Dieball. Right, because I went to an aldehyde, must be Dieball. I'd put this third example here, or fourth example here, just to kind of make sure that we cover this. The Dieball is a good reducing agent. It will reduce, in this case I have a ketone. There's no reason it won't reduce a ketone, right? It will chelate to that carbonyl. It will then make an active hydride, and that active hydride will just attack your ketone. There's no reason why it wouldn't. And so this would just reduce your ketone to make the alcohol. You know, it still works. It still adds 1 hydride. Normally we would use something less expensive and easier to work with, like sodium borohydride, but you certainly could use Dieball for that. And so you want to pay attention that you don't accidentally reduce things that you don't mean to reduce. Now this last one is a little bit of a synthesis problem. If I take a look at this, I definitely notice that I formed an aldehyde. Right, I formed an aldehyde here. There was a chlorine, now there's an aldehyde. And if I look closer, I also see that if I call this carbons 1 and 2, this is carbon 2 and 1. It looks like I have a new carbon. I added a new carbon. So also I have 1 more carbon. So I must have done this from a carboxylic acid derivative. Probably did it from a carboxylic acid derivative. And then I reduced that carboxylic acid derivative to the aldehyde. So for this one, I would say maybe, you know, you could use maybe just add sodium cyanide. That shouldn't affect the thiophene. So now I have C triple bond N. And I know that if I do step 2, I do a hydrolysis. Say I add acid and water with some heat. That will turn that nitrile into actually, whoa, let me back up. I don't need to do that yet. I've got a nitrile. Let's just go ahead and add our Dieball. Let's save ourselves some work. So then step 2, let's just go ahead and add our Dieball, which is going to add that 1 hydride, right, which is going to add this H. And then step 3, let's do the hydrolysis. Excuse me. Then let's do the hydrolysis so that we can turn that imine back into the aldehyde. And that would get us from point A to point B. And so if you do find that you're working with carboxylic acid derivatives and you need to turn one of those highly oxidized carboxylic acid derivatives down 1 step to a aldehyde, Dieball is probably the way to go. If you're reducing it down 2 steps, then you're going to use LAH. So that's kind of the difference between the two of those. Definitely practice this. Study. Good luck.